All right, so we're going to move on to section 22 in the textbook now. And this section is concerned with some more topological concepts, mostly revolving around the concept of connectedness, which is a property that we can assign to various sets in a topological space. And it has actually a very elegant definition. And it really is just, I mean, connectedness is what it sounds like. It's like, when can you say that a set in a topological space is actually one big piece and it's not two, like multiple different pieces, totally separated from each other, basically, right? And it's not enough for two sets to be disjoint for them to be disconnected, right? Like, because like you could have something like uh like A, B, and then like B, C, right? Uh, these are not separated from, each other because, well, they touch, right? They kind of like are right next to each other, and there's no points, there's no gap. There's no gap between them, right? No gap between them, right? But A, B, and B, C are separated. So because there's a missing point, right? Missing point in between, right? So if we had a set that was like the union of these two pieces, right? The set that's the union of these, right? The union is just AC, right? One piece. It's just one piece. In this case, the union is AC without the point B, which is two pieces, right? It's separated at this point B where there's like this missing point, and that separates the set into two disconnected pieces, right? Another way of thinking about it is that you couldn't get from one side to the other without like crossing a point that's not in the set. Versus this one, you can get from one side to the other, and you never, without ever touching a point that's not inside the overall set AC, right? So okay, anyway, so how do we formalize this idea? That's the idea of connectedness. So let me state the definition. So this is 22.1. So yeah, let E be a subset of a metric space, right? S is a metric space. We say E is disconnected if there exist U1 and U2 open subsets such that well, okay, yeah. I mean, so there are two equivalent ways of defining connectedness, and they just get stated in the same definition here. So, well, okay, I'm going to state this one first. Okay, so so E intersect U1 intersect E intersect U2 is the empty set. So they're, disjoint, basically. U1 and U2, the idea of U1 and U2 is that they're sort of supposed to separate the two pieces of E. And so, they shouldn't overlap with each other. I mean, there are intersections with E, right? The intersection of U1 with E is like the piece of E that's in U1, right? The intersection of U2 with E is the piece of E that's in U2. There should be no overlap between those two pieces of E, right? Because U1 and U2 are supposed to like sort of show that E is disconnected. So this is true, and E union, or sorry, not union, E intersect U1 union E intersect U2 is all of E. Okay. So that just says that basically U1 and U2 cover E, right? So like all the points are accounted for. There's nothing missing. So that way there can't be any sneaky points that actually like connect the two pieces together, but they just happen not to be in either of these two intersections. We don't want to let that happen. And then, of course, so yeah, also each of these two pieces should be non-empty, so you can't cheat. E intersect U1. It's not. And then E intersect U2 should also not be empty. Otherwise, every set would be disconnected because you could just take one of the two subsets could just be the empty set. So yeah, we want to prevent that from happening. So let me just kind of draw a picture of this, you know. Okay, so I tried to just sort of draw a random set. So this piece here, there's like, you know, so like, let's say this is U1 and then this is U2, but this is like E intersect U1, and this would be like E intersect U2 is over here. And so like these hard edges are supposed to be kind of like, you know, like this is filled in and this is like a closed boundary, but then part of it is also open over here. And then there's some random points. This is a curve. Here's like an open boundary and then this filled in area. And then also like a piece of it is a closed boundary. And then there's like a cluster of like dense points over here. So you can see, you know, there's like a lot of different shapes that E could have, but ultimately it can kind of just be separated into two big open sets, right? And notice that it's actually okay if the open sets themselves, right? So that we could have like a piece of E, so maybe this is E intersect U1, and then this is like E intersect U2, and then like the open sets themselves could actually overlap. That's okay by our definition. It's okay if the open sets overlap, as long as the intersections with E don't overlap. Okay, that's the key. So there's overlap between U1 and U2, but the intersections with E don't overlap. All right. So there's another equivalent definition of this. Or equivalently, E is disconnected. Whoops. If we can write E equals A union B, where the closure of A intersect B is the empty set, or sorry, is the empty set. The intersection of A with the closure of B is the empty set. So this is kind of ensuring that they're, you know, not touching. Because that way, like, you know, if there are points in the closure of A that were like that were actually in B, then we would have that scenario like with you know, in this scenario, right? There's a point in the closure of this set, which is you know, B itself, which is actually in the other set, right? So that's the sense in which these two sets are touching. This is actually like the appropriate like abstract formulation of that idea. And then yeah, oh, that's actually it for this version. Right, so this one, I don't know, it's a little bit nicer to state, I guess, but I actually kind of personally prefer the other one. I think it's easier to work with in most contexts. But here let's just sort of quickly prove that that the two definitions are equivalent. So sorry, I forgot to mention that A and B have to be non-empty here. So the idea behind the equivalence of these two definitions basically boils down to the idea that like A and B basically in this version of the definition, A and B are effectively playing the role of E intersect U1 and E intersect U2, right? Like E intersect U2 is U1 is supposed to be the piece of E that's in U1, right? So it's this like piece of E over here. So that's basically our set A, which is supposed to be a subset of E, right? A and B are like subsets of E, and their union together makes up all of E. So in this case, like, oops, A would be like this little piece of E here, and then B would be like this other weird piece over here in the blue set, right? Not like, yeah, well, yeah. So that's the concept behind why they're equivalent. So um, let's just prove they're equivalent. So suppose the first version holds, then set A equals E intersect U1, B equals E intersect U2. Okay, and then so clearly A and B are non-empty and disjoint, right? Since by this definition, right, A and B have to be non-empty. Like this is A and this is B, so they have to be non-empty, right? So now we just have to show that the closure of one never intersects the other one. So we can just show that A closure doesn't intersect B. So suppose, I guess they call it B. Suppose there's an element of the intersection here, right? So the idea is like, okay, if B, so here's like B, right? And then there's this like open set U1, right? And then here's like A, and then there's this open set U2, right? Now, B is supposed to be in the intersection of the closure of A and B. So B is like somewhere over here. Let's say B is like right on the edge here. And then somehow actually A is able to come up and kind of like get really close to B, right? Like as you can see in this picture, it's impossible to do that without part of A crossing into the set U1, which is not allowed, right? And the reason for that is because no matter what, any point in B, since it's inside of U1, it has to be interior to U1. So there has to be like a radius around this point in B where all the points in that radius are in U1. But if the point is also in the closure of A, then there are points of A that have to be inside that radius, which is a contradiction. So let's just put that, let's formalize that. So then there exists R greater than 0 such that BR of B is a subset of, or sorry, this is U2, sorry. U2, U1, U2, U1, right? So that's just because B is inside of capital B. Capital B is a subset of U2. U2 is open, so B is interior to U2, right? So this R exists, and then, but then there exists an A in BR of B. This is because B is in the closure of A. So, and A is in A as well. This is a contradiction because A can't be, right? Because this also means that A, so then, right, A is in U1 and A is in U2. We can't have that, right? So so that's going one way. So that's like, if we assume that this this definition holds, then the second one holds. Now we'll go backwards. So let me erase this. All right, so now we're going to go in the other direction. It's hard to draw a picture for this, unfortunately. So you'll just have to kind of try to visualize, you know, what the symbols are saying. But in this case, right, the idea is we start with A and B, that satisfy these properties, and we want to come up with U1 and U2, right? We want U1 and U2. And those are supposed to be open sets, right? Now, A and B, we don't know anything about. We don't know whether they're open or closed, both or neither. They're probably neither open nor closed, right? So in situations like this, like often the way I think is just like, what are some open and closed sets that I even have access to, basically, right? Based on A and B, what open and closed sets can you get, right? Well, one open, if we're just going for open sets, we could try for the interiors of A and B, right? But the problem about that is that, like, most likely A and B are super weird, and probably their interiors could just be empty for all we know, right? I mean, in this picture, right, the interior here, like this weird dense cluster of points, the interior is probably empty of that. The interior of that part, right, is probably empty. So we're going to lose a lot of information about A and B by doing that, and we probably won't end up with any useful sets. However, we also have access to some closed sets which actually appear in the definition, so that should sort of pop out to us, right? A closure and B closure are in the definition. Now, to get an open set from a closed set, you take the complement, right? So it turns out that we can take U1 to be, let's say, S complement, the complement of, of the closure of B. And U2 can be the complement of the closure of A. Okay, then, so clearly, E intersect U1 intersect E intersect U2 is empty because, right, so E intersect U1 is just A, and E intersect U2 is B, right? Because A, so like every point that's in U1, or every point that's in E intersect U1 can't be in B, right? And any point that's in A is automatically not in B, but it's also in E, right? So yeah, I mean, just, I don't know, sorry, I kind of tripped over my words there, but yeah, if you just think about it, like the points in here are exactly the points of A, and the points in here are exactly the points of B. So, oh, right, yeah. So that's, so yeah, this follows because A intersect B is clearly empty if their closures never intersect each other. And then also, yeah, so yeah, E, well, I'm not going to write it. So, okay, right, E intersect U1 is A, E intersect U2 is B. Also, E intersect U1 union E for the same reason, because this is A, this is B, and then E intersect U1 is not empty, and E intersect U2 is not empty, because this is B and this is A. Okay, so yeah, that's exactly what we want, and that should do it for this little proof here of the equivalence of these definitions. And then the last thing I want to do is just give one example of, actually, no, you know what? I'll make a separate video for that. Okay, so that'll be it for this video.